And welcome to Study Guide for Physics 135B, Module 2, where we're going over how to work these problems. And I've given an instruction here, which is to work each problem before checking your answer with the key. So this video will be posted on Moodle, but if you're watching this video and you haven't yet completed the study guide, keep in mind it's a very good idea to take your best shot at every single problem before watching the solution. Because if you do that, then the way our brains work, we will actually learn more once we investigate the solution by comparing what we've done to the solution. So with that being said, let's move forward to the memory bank where we talk about relevant equations that we've covered thus far in the course. This represents the majority of the course. There's a few topics to be introduced after what we've achieved in this list, but this is quite an extensive list. We've got volume and density, the Coulomb force, different constants of nature. So you have the K constant, which is really 1 over 4 pi times the permittivity of free space, and that's got certain units that work out to within a few percent, 9 times 10 to the 9 newtons per coulomb squared times meters squared. And the charge of an electron in item 5 there. Just a reminder about what the atomic mass is if we set out to calculate how many free charges there are per unit volume in a conductor, for example. And then the definition of the electric field as it pertains to charge, force, etc., and the electric field for a particular charge configuration to oppositely charged planes of charge with density sigma. The actual value of the permittivity of free space once we know it is a farad, the unit of capacitance. And then the definition of potential, that is the voltage, in terms of potential energy and charge, Q and U. So the relationship is that the energy is given by the charge times the potential energy per unit charge, aka the potential. And then most ideas flow from there. That is the definition of potential can be used to describe E fields as the slope of voltage, and in a capacitor there's a linear E field or a constant E field that points in a certain direction with a linear voltage dependence. Then we can define the relationship between stored charge in a capacitor and the potential required to gain that charge as the capacitance. And for the capacitor made of two plates of charge, there's a particular formula for the capacitance. Adding capacitors in series and parallel, there's certain patterns to be memorized there. And then when we can define current, it's the ratio of the change of charge divided by the change in time. And we had a little side discussion about just how quickly does charge drift through wires if it's being pulled by a voltage. And that's actually an interesting topic about microscopically what does current resemble. But you can think of it as like water molecules and the motions of water molecules in a liquid as there's a flow of water. And it's the velocity of charge, however, in conducting metals is a little bit slower than what you might experience in a trickle of water, because there are many, like almost an impossible number, like Avogadro's number of charges, individual charges moving. And so to get the current that we observe, you don't need a very fast velocity of charge movement in the direction of the current. Now, when current flows through devices and powers them, we quantify that relationship between potential and current flow as resistance. And resistance adds together, in different ways depending on whether the circuit is in series or parallel. And then once we know, resistance and voltage, we can calculate the current and then derive the power consumption of a particular device. Now, we didn't cover RC circuits, so I'm gonna skip item 26 and 27. But we did cover Kirchhoff's rules. So items 28 and 29 merely reflect that charge is conserved and that energy is conserved in loops within circuits. Now the study guide begins with a problem regarding um, force on charge, and it reads two charges exert a force Fc of 5 newtons of force on each other. What will Fc be if the distance between them triples? Now, the relevant a piece of information that you have to begin with which you have to begin is that this is a scaling problem, and scaling problems do not give all the required numbers to plug into a formula, solve for the one unknown variable. Actually, we rarely want to do that in real life. In fact, most of the time, solving a physics or engineering problem, or as those kind of problems arise in your field, uh, usually follow some sort of pattern, and you have to apply it to this specific case without knowing all of the necessary information. So if you recall the actual form of the Coulomb force, it's Q1 times Q2 divided by the distance between Q1 and Q2 squared will be the magnitude of the force. But if you think about how it actually depends on distance r between the charges, then if r becomes 3 times r, if r goes to 3 r, well then that means that r squared goes to 3r squared, which is equal to 9r squared. And so if r triples, then there will be another factor of 9 down in the denominator. And so the force will go down by a factor of 9 if suddenly there's a new factor of 9 in the denominator. And so if it was 5 newtons, then it should become 5 divided by 9 newtons, because that would reflect the fact that force goes as 1 over distance squared. A tripling of the distance will decrease the force by a factor of 9. And then part B requires us to make some more room. But it says if one charge is 1 nanocoulomb and the other charge is 2 nanocoulombs, what is the distance between them if Fc is 5 newtons? So in this case, the most prudent course of action is to solve for the distance. So we know now Q1 and Q2 and the force, and we also happen to know K. And so if we simply write the Coulomb force is K Q1 Q2 over R squared, solving for R squared is equal to 2K Q1 Q2 over F. Whatever the force is, happens to be 5 newtons in this case. And then taking the square root of both sides yields R, which is K Q1 Q2 over FC, and then we're taking the square root of everything. Now it gets interesting because we have to plug in real numbers. And K, the value of K is 9 times 10 to the 9th newtons per coulomb squared meters squared. So let's keep track of units actively. That's always a good strategy. The units should work out to what exactly is on the left-hand side of the formula. So we have 9 times 10 to the 9th power newtons per coulomb squared meters squared times Q times Q. So it'll be 1 times 2. So let's just put a 2 there. But then they were nanocoulombs. So if we want to work with coulombs here, we have to have just coulombs and not nanocoulombs. So there's a 2, and then we have 10 to the minus 9 for Q1. And it would, if we were to convert it from nanocoulombs to coulombs. But then we have another factor of 10 to the minus 9 as well for the other Q. And then we're dividing by 5. We're dividing by 5 newtons only, and taking the square root. Now, this factor of a billion cancels this factor of 1 1/billionth. And then all the units cancel. The units of K are here, but then we're multiplying by 2 charges, so those go away. And then in the denominator, So we had a Coulomb squared for each of these charges, right? Coulombs times coulombs. But in the denominator, there's a force, and it's 5 newtons of force, and so that newtons canceled by that newtons. And the only remaining unit is meters squared, but remember, we're taking the square root. So the overall result is that R is the square root of 9 divided by 5 times 2. Right, 9 times 2 divided by 5, and then there's an unresolved times 10 to the negative 9th power, but then we're taking the square root of everything, and the units are meters because it's the square root of meters squared. So 9 times 2 is 18. Let's see if we can work this out by hand. 18 over 5 square root times 10 to the negative 4.5 power meters. And I say that because it's 9 over 2, so the 1/2 multiplies the negative 9 to become negative 4.5. So if we work out what is 18 divided by 5, that's 3.6, and we'll take the square root of 3.6 to obtain about 1. Let's go with 1.9. So that's R is equal to 1.9 times 10 to the negative 4.5 meters. So what if we were to simplify that to get the actual answer in some recognizable unit? You can always use Google as a calculator. So let's say 10 to the negative 4.5 power, and then while we're at it, 1.9. And so that's a really small power. Let's divide by 1 times 10 to the 6th. What I mean is multiply by 1 times 10 to the 6th. That will put the answer in microns. So that's 60 times 10 to the negative 6 meters, right? 60 times 10 to the negative 6 meters, and 10 to the negative 6 is actually called a micron. So you can write in fancy notation 60 micrometers. So very very close together, but not so close that you would consider that the length of a molecule. So okay, so that was more of solving for R, taking the Coulomb force and solving for R. But now let's consider problem 2. The classic Millikan oil drop experiment was the first to measure accurately the electron charge. So oil drops were suspended against the gravitational force by a vertical electric field. So in the diagram, it's like, this, if this were a positive charge, it would be pushed downward by both gravity and the electric field. But if it's a negatively charged object, it's attracted to the positive plate. So it will have an electric force. Oh, I guess I can't. It'll have an electric force, F Coulomb, but then it'll have a gravitational force, Fg, and those two things will balance each other, and so the object could remain still. Now, in real life, the droplets would either accelerate up or down, or some of them would remain still, and so the accelerations up and down and the particles that remain still were measured in their diameter, and then also the force required to suspend such a droplet was quantified and plotted against, the different accelerations, right? And that would reveal the differences in force. Even if it was 0, it would reveal the differences in force, and those differences were discrete because there's only so many electrons on the droplet. So let's calculate the weight of the drop. We're going to need the very first formula in the memory bank, that mass is equal to the density times the volume of an object. And the volume in this case, that's the density, and the volume is 4/3 pi times the radius cubed. And that's all the algebra that we can do. We really have to just plug in now. I suppose we could do one more step, which is that if we're specifically looking for the weight of the droplet, then that weight means force, and the force of of gravity downward is mass times the acceleration due to gravity, which is g. So mg downwards is the weight. Let's call that weight w. We have to multiply whatever the mass is times g, so that's rho g times 4/3 pi r cubed. We could find the number for the weight. If a droplet has a single excess electron, find the electric field strength needed to balance its weight. So at that point, I'll return back to the algebraic expression and solve for the electric field first before moving forward. So the weight here will be the density rho, which is 920 kilograms per meter cubed. And then g, let's say, is 10 meters per second squared. So we'll say 10 meters per second squared. And then 4/3 pi, or 4 pi over 3. Now we come to r cubed, but remember that the droplets have this radius in micrometers, which, as we described earlier, is actually 10 to the minus 6 meters. And so if r is equal to 1 micrometer, r cubed will be equal to 1 micrometer cubed. So that's 1 cubed is just 1, but now we have micrometers cubed. So a micrometer is 10 to the negative 6 meters, and 3 times 6 is 18. So this is actually 10 to the negative 18 power meters cubed, right? Because, again, this micrometer just stands in for 10 to the minus 6 meters, and so it's cubed. So it becomes, to get it to meters cubed, that's 10 to the negative 18. Those will be meters cubed. Notice the meters cubed cancels here and here, leaving kilogram meters per second squared, which is actually a Newton. So do we have any numbers in the denominator? Yes, we do. We have the 3 there, so it's 9,200, which is the 10 times the 920 times 4 pi. Then divided by 3 only, 3, times 10 to the negative 18th power, and that will be newtons. So quickly I could calculate what is 9,200 times 4 pi divided by 3. And then that's going to be something like, right, like almost 4 times 10,000. So W will be equal to 4 times 10 to the 4th power times 10 to the minus 18th newtons. Now, negative 18 plus 4 is negative 14, so W is equal to 4 times 10 to the negative 14 newtons. Notice I'm only keeping one significant figure. I think that's all that's required in this problem, because the idea that we would be able to measure force that accurately at that scale, that's a very difficult thing to do. Now, that's the weight of the drop, but find, if the drop has a single excess electron, find the electric field strength needed to balance the weight. So let's return to that formula, because if the weight is equal to rho g times 4/3 pi r cubed, well, if the weight is that, well, you have the weight 4/3 pi r cubed, and that's equal to the force of the electric field on the charge. That's QE. And so if we divide both sides by Q, we have E, that's equal to rho G divided by Q, rho G divided by Q times 4 over 3 pi r cubed. So it's the same exact as the weight, but we divide both sides by Q, so there's a Q now in the denominator. That becomes the E field expression. So this would be 4, it's the weight, right, divided by Q. So it's 4 times 10 to the minus 14 newtons, but then we're dividing by the charge. But what's the charge? It's that of a single excess electron. So the charge of an electron, as it's shown in the memory bank, is 1.6 times 10 to the minus 19 coulombs. Now we have the right units because the units of an E field are newtons per coulomb, or if you will, volts per meter, but newtons per coulomb are the first units of the E field. And so our E is 4 divided by 1.6 times 10 to the negative 14 plus 19 newtons per coulomb. Now, 19 minus 14 is positive 5, right? So it's actually, I need to know what is 4 divided by 1.6, which is 2.5. So that's 2.5 times 10 to the 5th newtons per coulomb. So the 5 comes from 19 minus 14. So 2.5 times 10 to the 5th, or 250,000 newtons per coulomb. So that's a force balancing problem, in addition to knowing a couple of facts, like, for example, that the force is equal to Q times E for the Coulomb force, or any electric field, really, but also that the force for gravity on an object of mass m is just F equals mg. Those are the key physics concepts from that part. Suppose two positive identical charges are located at a distance d apart. Sketch the electric field, so they're both positive now. So let's not get confused. Let's make sure we draw a straight line. And then we need to place our charge here and our charge here. And let's say they're both Q. Two positive identical charges located at a distance d apart. So sketch the electric field. Well, I argue that by symmetry, all along the line of symmetry between the two charges, that is halfway between them along a vertical axis, the E field is either 0, right in the middle, so that's where it's 0, but then it points this way, strictly vertically. As you go farther away, it gets weaker. Why do I say it has to be strictly vertical? Because you could be like at this point right here, and the horizontal components will cancel because this charge will push to the left as much as this one will push to the right. And so by symmetry, the electric field should be vertical there. Now, if you're closer to this charge, the field will be stronger, and it'll push away from this charge. So very close to this charge, it'll push like this. If you're here, that. If you're down there, right here, this one will push that way. This one will push that way. If you're very close to this charge, so close, in fact, that you can't really see the other one, then it would look, like get away from me and radially. But if you're over here, of course, then this charge will push that way, but then so will this one. This one will push the other way as well. So it would kind of be a combination of that. By symmetry, it'll be that, and like that. So actually, it starts to look like not that second line. It starts to look like the fields do this. So they want to be vertical on the y-axis. They go directly away from the charges if you're close to them. but they are bent by the presence of the other charge. This is known as a dipole. So any field that looks like that, where the sketch has the right properties, it's got purely vertical E field along the vertical axis, and as you go close to the charges, it looks radial, pointing away from the charge. And as you go very, very far away, of course, there has to be no electric field out here, because the farther away you go from the charge system, then the weaker the E field is. We get that from the Coulomb force, where the distance dependence is 1 over the distance squared. So that concludes the first section of problems, section 2, electric charge and electric fields. Stay tuned for potential energy and voltage.